Okay.
Thanks very much.
Continue. Thanks very much. Thanks very much, Chris. Yeah, it's a real pleasure to be here, to be permitted to give a discussion in this workshop. Because for me, well, it's a funny thing, really, because this is meant to be about conformal field theory. Sorry, did somebody say something? Hello? Sorry. Okay. Well, for me, it was actually sort of quantum field theory which got me into Painleve equations originally. So I started out, quantum field theory was or quantum theory was my first love as an undergraduate student into studying mathematics, and then in my PhD I set out wanting to study quantum theory and then quantum field theory, and then that led me to correlation functions and random matrix models, and then that led me to Painleve equations, and in the end I got stuck fascinated by the classical equations of motion rather than the quantum ones, more in a way. But I've always loved quantum theory as well, and I'm only just sort of getting the opportunity to catch up with all these developments in how conformal field theory relates to Painleve equations in this. It's a great opportunity, this workshop. So I don't know what the audience is going to be like today, and I don't know if they're experts, and but hopefully there's going to be a mixture of people, and I don't want to sort of introduce things to people that know them already. But if there's anything that I say that doesn't make sense, then please stop me and interrupt, and I'll try not to speak for too long, because it is meant to be a discussion. So I'd like the audience to sort of participate as much as possible and throw in, especially if they disagree or they have a question or whatever. So please do butt in with your microphone when you have something to say. Okay, so I'm going to start off really talking about some work that I did originally with, starting with Orlando Ranisco and Federico Zullo, and then it was just sort of me and Federico Zullo, and I said it was recent. Well, time seems to go faster and faster the older you get, so I think it's already three years old, the last paper we wrote with Federico. But the idea was really sort of looking at just the local Laurent expansions of Painleve equations around movable poles. And originally it was we started with Painleve 1, and then it was sort of easily extended to Painleve 2 and Painleve 4. And in some sense, you could say that the spirit of what we were doing is sort of contrary to this workshop, in a sense of asymptotics, because we were really trying to look at exact results and exact expansions, and I'll try and explain what I mean by that. And also what we were trying to do was trying to somehow make an exact analogy between elliptic functions and Painleve transcendence, in contrast to the sort of asymptotic results relating Painleve transcendence to elliptic functions, which will go back to Boutroux, and which Davide Massera described in his discussion. So let me just proceed then. So the first thing, so just an outline of what I'm going to say. So there's a kind of arithmetic of pole expansions for Painleve 1, 2, and 4, in principle, also it should extend to the other Painleve equations, but that's something we could come to later in the discussion. But there's no particular reason why it wouldn't work in the same way, except it just becomes a bit more complicated. And arithmetic in the sort of sense of number theory. So in a way, we're trying to, it's sort of connecting these expansions to things like, well, as I said, to elliptic functions and modular forms. And there are some sort of curious arithmetical properties of these expansions, which even for the elliptic functions are not completely understood as well. So there's quite some open problems there. Then in sort of coming out of that, there's sort of a couple of other ideas. So again, this is just a discussion. So it's just, again, it's sort of trying to throw out open questions. So there's sort of a question about heat or Schrodinger equations or Fokker-Planck equations or whatever what you want to call them, that are related to these, to the tau functions of the Painleve equations, or their wave functions, the wave functions of the isomonodromy problems. And yeah, I think there's a connection with string equations in quantum gravity, which is how I first sort of came to Painleve equations myself. So I'll try and say something about that. And then finally, it's sort of a question of my own about the exact structure of the wave functions for the Painleve equations in whichever choice of isomonodromy problem you take. So we did have some discussion about this before. This was a question that I was asking to David actually, about the choice of isomonodromy problem. But I think there might be something more to be said there as well. Anyway, so but it's maybe just to do with my ignorance, but it's more like a question to the audience as well. Okay, so here's some more questions as well that are sort of relevant to the discussion. So the first time I came to the Newton Institute was in 2001. And well, Martin Kruskal I met a few times before that, but one of the things that he liked to ask people when they were talking about Painleve equations in that meeting back in 2001 was, what's the point of having a time-dependent Hamiltonian if it's not a conserved quantity? Okay, so I think there are lots of answers to that, and we can discuss that. If well, I'll try and show what the use of the Hamiltonian is for Painleve equations, just for illustration. It'll come in my discussion. But anyway, I thought that was also nice. He always liked to throw the cat among the pigeons, and that was a nice thing he liked to be provocative, was to sort of challenge people. Well, why are you using this Hamiltonian if it's not a conserved quantity? But actually, in a way, also another question he asked, which also I think Sasha Veselov told me, Alexei Shabat also was sort of thinking about the same thing. Was he just suggested, well, if you've got this tau function for the Painleve equations, for a Painleve equation, isn't that useful also numerically if you want to calculate the poles? So just because the tau function, if the Painleve equation is meromorphic, well, the solutions are meromorphic in the neighborhood of the poles, or even globally meromorphic for P1, 2, and 4, then the tau function is holomorphic, and so you just have a holomorphic function, so it's analytic on the whole complex plane. And why not, directly analyze the tau function and use that to find the poles, to analyze the poles of the solutions of the Painleve equation. And in a way, that's the simple idea, which basically is what we did in this work with Ranisko and Zula originally. So we're just directly analyzing the tau function. And then another thing is just more generally, is just to say, well, what about Painleve transcendence, their initial value problems? Can we really, we have all this framework of isomonodromy and so on, and can we describe the explicit solution of the initial value problem? And I remember I had a conversation with Sasha Itz some time ago. I don't remember exactly when, but he was almost horrified by this question. He said, "That's you can't ask that question because with the isomonodromy approach, we can only really understand asymptotics and connection problems, and that's the only thing that we can really, that's possible." He said it's the wrong question to ask, but I think that may not be true anymore. I think now that we have this Kiev formulae, we have very explicit, potentially very explicit expressions for tau functions of Painleve equations, and therefore we can really think about them as special functions, in the tradition of special functions, say Abramowitz and Stegen, that we can write down lots of explicit formulae, and we can really calculate things explicitly and exactly. Of course, the thing is, nowadays, with numerical computation being so efficient, that you might say, well, do we need explicit formulae? So that's another question for discussion. Another philosophical question is that if we can just do a very high precision Runge-Kutta method, then isn't that as good as having some very arcane and complicated explicit formula for our special function? So again, that's a question I'd like the audience to discuss, maybe at the end, when I've maybe that's one of the things we can discuss. So please try and keep some of these things in the back of your mind before I confuse you further. Okay, so let me say something about the sort of main topic of my discussion. So I want to start with the coalescence cascade, which was in Albert Grassi's beautiful talk at the beginning of the workshop. And so on the top, you have the top row, or the top level, which is P6, P5, and P3, which comes in 3 different flavors, but I haven't put them all, the separate types of P3 separately. I just put them as one P3 on its own. And then there's the lower level, which is P4, P2, and P1. And so, as I said, I'm very much a novice about conformal field theory and this Kiev technology. So I'm just trying to understand it myself at the moment, and trying to learn it from this meeting. But as I understand, so the top row is where we have these amazing formulae which express the tau functions of these Painleve equations as Fourier series in one of the monodromy data, and the coefficients are essentially these conformal blocks that come from a C equals 1 central charge equals to 1 conformal field theory, and then there's some sort of quadratic term in time as well, and then there's also a Barnes G function terms in the denominator. So I should have written that down, written an example down, but I think everybody in the meeting probably has at least seen this formula. But apologies if you haven't. I can dig out the formula if somebody hasn't seen it. So there's this amazing explicit formula for the tau function, and for me, that's very reminiscent of a theta function. I mean, it's a bit more complicated than a theta function, but it's not much more complicated. So it's a Fourier series, and the one of the Mondromi data replaces the modular parameter tau, if you like, and then there's a quadratic part, if you like, in the and then there's some other, if you like, the Fourier coefficients are more complicated, but it's not much more complicated than a theta function. So that makes me think about analogies between, as I said, between elliptic functions or theta functions, modular forms, and Painleve transcendence, and that there are more ways that we could exploit these analogies in the future. But then, as I learned from Albert Grassi's talk, is that on the lower level there isn't a nice conformal field theory structure that's known. There's a hint of what the theories should be, but there's not a nice formula. So it's sort of curious that it turns out that in the work that I did with Zula and Renisco, or mainly with Zula, that we ended up at the lower level and not looking at it. I think I was sort of I sort of noticed this from when I met Oleg Shisovi, that somehow sort of complementary what we did, but it doesn't fill in. It doesn't give a formula of the type that one might want. Okay. So okay, then I'm just sort of giving you some basic background that everybody, as I said, I'm sure everybody knows, but this is going to appear quite a lot. So Okamoto showed that the Painleve equations can be written as non-autonomous Hamiltonian systems. So they're just 1 degree of freedom Hamiltonians. So I've just written down the Hamilton's equations for a Hamiltonian Hj, which is labeled by the Painleve equation, and but the Hamiltonian depends explicitly on the independent variable, on the time, which is z in my notation. So I've given you the example of Painleve 1. So I've perhaps written it in a slightly curious form. So W is the dependent variable of P1, and then I've put 2 parameters, lambda and G2, and they're both constants, and they're supposed to be, well, the G2 is supposed to remind you of elliptic functions, because of course if lambda equals 0, then this is the equation for the Weierstrass P function, the Weierstrass elliptic function. Okay, and then I've just written down what the Hamiltonian is with a canonical Q and P. So Q will be W, then well, Q will become W, the dependent variable of the Painleve equation. So the Hamiltonian looks like this. It's a natural Hamiltonian, but it's just that the potential here depends on Z, which is the time. And then I've also put plus constant because actually we might want to add on a constant, and in fact we will do that in a sense. So let me just tell you why I've done that in a minute. Okay, so the point is, yes, Hamilton's equations, it's easy to check that they're equivalent to the Painleve 1 equation, the simplest Painleve equation. But then also, of course, if you differentiate the Hamiltonian with respect to time, then that's the same as the partial derivative with respect to time for a time-dependent Hamiltonian. And then, so that gives you the derivative of H in terms of Q, and then the second derivative is basically P, the momentum. And then, so if you rewrite, so you could, well, there's two things you could do. So you could substitute in the Painleve equation with W being H prime, and that would give you a third order equation for H. Okay, so we will see that equation in due course. But the other thing we could do is we could actually just substitute for P and Q directly into the expression for the Hamiltonian. So if we do that, then what we would get is a half of, okay, I'm going to drop the index, but H double prime squared. I've got this annoying lambda factor here, which is going to make my life a pain, but okay. And then minus 2 H prime cubed over lambda cubed, and then plus lambda Z plus a half G2 times H prime, and then plus a constant. You see the the constant, I will fix the constant later on, but let me just put right constant, and that's equal to H. Okay. So this is what's called the sigma form of Painleve 1. It's a second order, second degree equation for the Hamiltonian. And all of the Painleve equations, if you write them in the Hamiltonian form, they have this sigma form. And as various people have pointed out in the course of the meeting already, it's actually really the tau function, or the well, it's actually the sigma form of the Painleve equation that tends to crop up much more in applications, rather than the rather than the original Painleve equation itself, either the sigma form or the tau function. And the tau function, well, the Hamiltonian is the logarithmic derivative of the tau function. So either the tau function or the Hamiltonian, in a sense, are really the central objects of the theory, especially when it comes to applications. And this constant, but coming back to this constant that I've put in here, remember that I said if you plug in W equals H prime, or Q, well, Q is basically the same as W, so from my, yeah. So if I plug that back into the Painleve equation, as I said, you get a third order equation for H. So that equation is what you get by differentiating this second order sigma equation that I've just written down. You differentiate, you can see you'll find you'll get a well, if I haven't made a mistake, I haven't made a mistake. But yes, you'll find that you'll get a third order equation. A factor of h double prime should just drop out. It may depend on my scaling of lambda actually, so I have to anyway. But never mind. If we certainly, it works if we set lambda equals 1. But the point is that this constant, so is, you can think of it as it's an integration constant. If we started with the third order equation for h, then then this third order equation actually has a first integral. And for those of you that know about singularity analysis, Painleve analysis, this integration constant is actually the first the resonance coefficient that you get when you do the singularity analysis around a movable pole for P1. So that's what that constant is, and I want to keep it there as part of my analysis of the equation. Okay, so we'll see how it comes in. Okay, so that's Painleve 1, and that's what I'm going to use. That's going to be sort of my main example to begin with, and then in due course I'll sort of talk about the other, well, the P2 and P4 as well, and how they combine with it. Okay, so as I said, I want to talk about the analogy between Painleve transcendence and elliptic functions, and the basic Boutroux asymptotic result is for large argument and approximating the solution near for large argument near poles. And Davide talked about this a bit, and in his discussion, and also Ovidio Costin also talked about this approximation problem of approximating Painleve transcendent, say P1 near to a pole, particularly the Tritranche solution. So this is the sort of basic asymptotic scaling that you can take from Boutroux. But what I would like to try and explain is that there's some other correspondence which is exact in a sense. And what I mean by exact is that that you can write down. So I mean, the result that we found in the end for P4 down to P1 is that you can write down a tau function that depends on 5 parameters, and it includes all the solutions of P4, P2, P1, and the elliptic functions in one function. And you don't get down to, say, from P4 for P2 by a coalescence limit. You don't need to scale any of the variables. All you do is set a parameter to be 0, or 1 or 2 parameters. I think it's maybe 2 parameters. My memory is, I'm a bit rusty on some of the details, so I won't try and tell you all the details because I don't have them all at my fingertips, but I can present to you the function and the equation. So it's a different I would argue it's quite different from the coalescence limit. I don't know if it's a known result, but it certainly wasn't known to us. So it's so let me try and explain it. But anyway, to carry on with the analogy to begin with, there's a basic lemma which you'll know if you sort of did any analysis, singularity analysis, is that so let's take P1 type equations. So the ODE, so let's say W prime prime equals 6W squared plus F of Z. Or I should say the solution, well, so has a single valued solutions in the neighborhood of movable poles. So let's if and only if the function f is linear. Okay. So this is a very simple thing to prove. I mean, then you can elevate it to a theorem, but the theorem is not so easy to prove. You can then say that the ODE has the Painleve property if and only if this f of f double prime is 0. Okay, so in a sense, there's two cases. There's the case when f is just a constant, and then that's what I called minus a half G2, and that's the Weierstrass P function. And then there's the case when f is linear, and then that's Painleve 1. But and of course, you can always shift Z if you like, to make it just to be, and rescale to just make it Z or minus Z or whatever, multiple of Z you prefer. So the point is that there's only P1 or the elliptic function. And so this is sort of part of the analogy of Painleve, between Painleve equations and elliptic functions, of Painleve equations as non-autonomous versions of elliptic functions. Okay, and so and it's as I said, it's an easy calculation because you look for your leading order pole behavior. So let me just say, so there's a double, oops, I'm sorry. Sometimes this pen goes a bit haywire. Okay, so you start off with your leading order behavior, which is the double pole, and then you write down the Laurent series around the pole, and then you find that unless f is linear, you'll get some logarithmic branch point. Okay, so that's basic at Z0. So you'll get logarithmic branching. So it's an easy lemma to prove, but then to prove the Painleve property is not so easy. I won't go in. That's a whole can of worms, and I won't go into that. But anyway, there's probably the most efficient direct proof is Steinmetz. We use the modern proof. It's use differential inequality, so that's a very sort of efficient proof of the Painleve property, which he has a nice paper that covers P4, P2, and P6 actually. Okay, but by direct analysis of the Painleve equations themselves, rather than using isomonodromy or some other method. Okay. Okay, so what we then set, so anyway, this is sort of the starting point. This lemma as well is really the starting point of the work that I wanted to discuss, because basically we set out to look at these Laurent series expansions that you get, and you know, see how they compare with the well-known Laurent series expansions for Weierstrass functions, and the Weierstrass P function, and then also the comparing the tau function for Painleve 1 with the Weierstrass sigma function. So that's going to be the main thing that I'll come on to in a minute. Okay, so now as I said, we can always get rid of, if f really depends on z, so it really is linear, it's not just a constant, we can always shift z and get rid of the one of the constants, so the G2, if you like, we can always get rid of it. But actually, you know, it's quite convenient to say, well, okay, I could study the equation w prime prime is 6w squared plus z and look at around a movable pole, but I could also you know, always shift the pole to be at the origin as well, and just study the equation with a shifted parameter. So that's in fact what we did, and obviously the two problems are completely equivalent, but it seems to be quite, I mean, this is sort of the key point. If you want to do what I said you can do, which is construct a sort of master tau function, which includes all the solutions of P4, P2, P1, and the elliptic functions, then you have to you know, allow these extra shifting of the parameters. So you say, well, you know, I fix a pole to be at the origin, okay, but obviously it's completely equivalent to shifting and rescaling to the sort of canonical form of the Painleve equation. So henceforth we're going to consider the equation with so let's say P1, for example, with these two parameters, so lambda and G2 that I wrote before, but we'll require that it has a pole at the origin. So we'll fix a pole to be at the origin. Okay, so that's the only caveat. So in a sense, it's like we've got rid of one degree of freedom by fixing where one of the poles is, but we've sort of regained it by sticking it into the equation instead. So that's basically what we're doing. So then now, what does the Laurent series expansion look like? Well, here it is. It looks like this sum of Cn with power is just a power. Now it's just a power series in Z, as I said, because we fixed the double pole to be at the origin. and the first coefficient is 1. I haven't bothered to write down what the first few coefficients are, but you know, they're kind of some of them are fixed to, some of them are 0. So let's see, C0 is 1, C1 is 0, C2 is 0. Let's see, I have got them written down here. Hold on a second if you want, but it's not terribly important. The main thing is that they're fixed, they're generated recursively, and they depend on well, so they depend on yeah, okay, so actually I can write, I've got them now, so let me write them down for you. So C1, C2, and C3 are all 0. C4 is G2 over 20. Depending on my choice of scale, which convention which changed between different papers, C5, I think it's lambda on 6, but anyway. And C7, C6, oh yeah, so C6 is the resonance coefficient, which is G3 on 28, and C7 is 0. And okay, so by that convention, so C7 is 0 is the way that I've written that recursion. It's an empty recursion when n equals 7. So that's, yeah. So what you see is that there's one arbitrary coefficient, which is G3, and that's the constant of integration that appeared on the previous page when I was talking about the sigma equation. That's the first integral that comes out, if you like, when you integrate P1 down to the sigma equation, and that's the resonance coefficient. Okay, so if you're familiar with the Weierstrass P function, then these two invariants, G2 and G3, which are modular invariants, you can write the P function as a power series around 0, which is so I mean, I'm just copying down the coefficients. So we've just sort of scaled everything to reproduce the standard Weierstrass theory, but then there's this extra parameter lambda. And so you can also see that naturally, well, if you know about modular forms, then well, G2 and G2 has weight 4 and G3 has weight 6, and in a way lambda is sort of an extra thing that appears for Painleve 1, so it naturally has weight 5. You can see that it naturally has weight 5, and so if you do this recursion, then you get a whole load of polynomials in so for the P function you get a whole load of polynomials in G2 and G3, which are modular forms of the relevant even weights. Only even weights appear, and then but for the Painleve 1 you get this sort of extra thing lambda, so you get polynomials in G2, G3 and lambda with rational coefficients, and they're sort of like deformed, I mean, they're polynomial, or you could say they're polynomials in lambda with coefficients that are modular forms. So that's another way to think about it. But otherwise, it's sort of remarkably similar. And another thing is the Mittag-Leffler expansion, so which I've just stuck down at the bottom there in red. So the Mittag-Leffler expansion looks identical, except that in the Weierstrass case, it's sort of simpler in the sense that the sum over the poles is over the lattice, is over a lattice. So, I mean, the poles lie on a regular lattice, but otherwise the expression is identical. The only difference is that so I don't know, have I written it? I think I've written it underneath. Let's see. Yes. So then the point is, you can expand these coefficients from the Mittag-Leffler expansion. You can write these CNs in terms of the poles, and in the Weierstrass case, when you have the lattice, it's easy to see why, for example, why you only get even values of n appear, because the opposite poles cancel each other out. And also these sums over inverse powers of omegas, the poles, they're absolutely convergent for n greater than 2 in the Weierstrass case, because that's easy to show, but that's the order of the equation. The Neverlinear order is 2, whereas for P1 it turns out to be 5 halves. But again, so you have these absolutely convergent sums over poles, but now it's when n is greater than 5 halves instead of 2, but otherwise it's very, very similar. And other people, I mean, Steinmetz and other people have done similar calculations for the poles of P2 and P4, and I don't know about the other Painleve equations, but I wouldn't be surprised if they've been done as well. Anyway, so that's sort of the close analogy, if you like, in this local Laurent series expansion about one particular pole. But this is obviously only local. But what information can you extract from it? Well, you can extract some quite nice information. So one thing is, so okay, I'll show you a picture now, because I'm sure you're all tired, and I shouldn't carry on too much longer. So let me show you a picture. How do I do it? This one. No, hold on a second. Can you see a picture of lots of poles, lots of dots on the screen? Can you see this PDF file? Please tell me if you can't, because can you see a picture of lots of dots?
No, I see the PDF, but I can see just a formula for the tau of Z.
Oh, okay, wait a sec. Okay.
Formula 31.
Oh, wait a sec. Here we are. Here now?
Yes.
Yeah. Okay, good. Yeah. Okay, so this is a particular solution of Painleve 1, and it's a solution that has five-fold symmetry, and it turns out apparently, so Kitaev found that there are 2 solutions exactly like this. One of them which has a double pole at the origin, which is this one, and another one which has a 000 at the origin, and you can explicitly describe the monodromy map for these 2 solutions, but apparently not for other solutions of Painleve 1. And this is obtained in a straightforward way by, so remember we have 3 parameters now. So we have G2, G3, and lambda. So if we just take G2 and G3 to be 0, then we get this 5-fold symmetry. And then the way that we generate this picture is by finding the tau function as a polynomial approximations to the tau function, which satisfies a bilinear equation. Actually, it's a sort of like the equation that appeared in Peter Clarkson's talk this morning, which is included actually within a larger equation that I'll show you in a minute. And then you just find the zeros of that up to whatever order. So in the middle, you get a good approximation to the poles. The boundary, obviously, you're no longer, you're looking at the roots of a polynomial and no longer really approximating. You've just truncated a Taylor series. So this is just the truncated Taylor series for the tau function, and you get these beautiful pattern of the poles of Painleve 1 with 5-fold symmetry in this case. Okay, so let me go back to what I was writing. Okay, so another thing that's rather interesting is that you can, I shouldn't spend too much. I should really move on and finish my talk in a minute. But I'm not sure how long the discussion is supposed to go. If the discussion is supposed to finish now, or actually, can you advise me? Is the discussion supposed to be only 1 hour, or is it supposed to?
There's not really a prescribed finishing time. You're welcome to continue on. Some have gone as long as 2 hours. So
Okay, I don't want to go on that long. I don't really want to go on that long, but I'm a rather slow speaker, and so I probably will need to spend a little bit longer to just say.
We're very happy for you to decide when enough has been said.
Okay. So, yeah, another thing that's interesting is if I can get it to work, is to. No, my pen doesn't seem to be working now, so this is a bit frustrating. Let me just try and share again. Yeah, I don't know. I'm having slight problems now with now that I've changed the screen share. It's not letting me. Okay, it's letting me erase there, but it's not letting me. I don't know. I wonder if these pens. I'll just put the pen back in for a minute and see if I can. Well, okay, I'm drawing with my fingers now instead of my pen, because the pen seems to be. Well, so my fingertips are not so bad at writing. There we are. You can read that. So another thing that's interesting is if you take the ratio of these coefficients, you can find, it's a sort of a little exercise looking at this expansion, that the nearest pole to the origin, assuming that there's, so you fixed a pole at the origin, and then assuming that there's only one pole, you know, one nearest pole, next nearest pole to the origin, let's say, then the limit of this ratio as n tends to infinity allows you to calculate the next nearest pole. And the recursion that I wrote above, which is quadratic in C, is you know, you can calculate it very fast. So you can calculate your poles near to the origin very quickly using this recursion. But I'm sure this is sort of technology that's you know, sort of standard it's sort of standard analysis anyway. But so that's quite fun to do. But now let me come on to the main thing about the tau function. So let me sort of okay, so that's everything for P1. Well, I didn't tell you all the stuff about the tau function, but let me generalize it before I tell you about the tau function. So I told you about the sigma equation, this second order, second degree equation for the Hamiltonian. So it turns out that you can, if you do the same procedure for P4, then you get a slightly bigger sort of sigma equation, which it looks like this. So this is what I'd call the master form of the sigma equation, and it's got five parameters: eta, kappa, lambda, G2, and G3. And you can see, for example, that if eta and kappa and lambda are all 0, then that reproduces the equation for the Weierstrass P function. Sigma prime it satisfies the equation, the Weierstrass P function. And then, as I mentioned before, the Hamiltonian, which is the sigma, the solution of the sigma equation, this capital sigma, is the logarithmic derivative of a tau function. So if you substitute in the logarithmic derivative of tau into the sigma equation, you get a degree 4 equation for the tau function. Now that's a bit unwieldy, but you can use that recursively to generate coefficients if you like. But yeah, that's very, it means with a computer, it's no sweat particularly. But what's more efficient in a way is to, as I said, if you take the derivative of the sigma equation, you have a third order equation. And that's a lot easier to handle. And that gives you a bilinear equation for tau, which is a Hirota bilinear equation. And this includes the Hirota bilinear equation for the Jablonski-Vorobev polynomials that was in Peter Clarkson's talk this morning. So the point is that by specializing these parameters, eta, kappa, and lambda, you get, you can get P2, well, really it's P34 is the natural equation that comes from the logarithmic derivative, is the people known in the ints as the P34 equation, which is a similarity reduction of the KdV equation, whereas P2 is sort of related by a Mura map to it and comes from similarity reduction of MKdV. So the point is that yes, this bilinear equation, it includes the things like the Jablonski-Vorobev polynomials, the rational solutions of Painleve 4 that Peter was talking about. Well, all the tau functions essentially of P4, P2, and P1. But also when you set those 3 additional parameters, eta, kappa, and lambda, to 0, then you get a bilinear equation for the Weierstrass sigma function. And this was studied by Ilbeck and Anolsky a few years ago, and they used that to generate the Taylor series recursively for the Weierstrass sigma function. Now the thing is that Weierstrass also looked at this, but not using a bilinear equation. What he did was he looked at a linear equation. So as you may know, the Riemann standard elliptic theta functions, or well, any theta function in fact, but the Riemann theta function satisfies the heat equation, where basically imaginary time is with imaginary time being the modular parameter, and the space being the other independent variable. So it would be z in this case, and so that gives you a sort of heat equation for the sigma function equivalently, which is another avatar of the theta function. That gives you a heat equation, but that involves derivatives. The modular derivatives become derivatives with respect to G2 and G3, and then you still have second derivatives in the argument Z. So that actually gives you a linear equation for the coefficients of the Taylor series of the sigma function. Now, this will be my sort of, I mean, I know I don't want to speak for much longer, so I'll just sort of try and summarize a bit now. But anyway, the point is, so we have a 5-parameter family of up to gauge, some gauge transformations, a 5-parameter family of equations that includes P4 down to P1 and the elliptic sigma function. So this is this equation for the tau function. And we can generate all the Taylor series recursively. So that allows us to give us the zeros, which gives us access to the poles of the relevant Painleve equation. And then we can write down this sort of master series. So let me, if my pen is working, because my pen just stopped working. I don't know if it needs to charge or something. But let me just otherwise I'll write with my finger again. Let me just see if I can write down one more formula for you, and then I'll try and summarize. Here we are. This is what okay. So I want to think about. Oh no, I'm on the eraser, but it looks promising. Okay. So function tau, the tau function, tau of z. So what does the series look like? It looks like so sum over non-negative integers, some coefficients, j, k, l, m, n. There's one index, an index for each parameter, and then we've ordered it as kappa k eta k half G2 L and then can I get the exponent in there? 3j plus 4k plus 4l plus 5m plus 6m plus 1 divided by, okay, it's going to be the same thing, 3j plus 4k plus 4l. So these integers are just the weights of each of the parameters that you can see. Okay, and so I claim that this function, which depends on 5 parameters, describes all the solutions of P4 down to P1 down to Weierstrass. Okay, all solutions are described by this sort of master tau function. And then what's rather interesting is the following conjecture. So this is where the arithmetic comes in, is that all the coefficients are integers. Okay, and I don't know how to prove that. So the point is that even in the Weierstrass case, when we set, if we set all the kappa eta and lambda to 0, it's still not proved in the Weierstrass case. So you can write down, so it's proved up to some powers of 2 and 3. I think Anishi has the best proof, but and using the linear relation, using the heat equation. So I mean, the thing is, there is one linear relation for the tau function, which is the fact that they have these scaling weights. There's an Euler operator, so there is one sort of relation that you get that simplifies. There is one linear equation in derivatives, which is just the scaling. But the question is there a heat equation for the tau function in all cases? And so, yeah, I sort of mentioned a few other things at the beginning, so I'll just sort of say what they are, because I left myself lots of space. So the question is, how could you get a heat equation? Well, there is so this is an observation of Kont and Dornit. So starting from the for P6 with the Fuchs-Lax pair, scalar-Lax pair, they show how you can derive a heat equation for the wave function for P6. So here's the scalar-Lax pair, and here's the heat equation, heat type equation, or whether you'd call it a heat equation or a time-dependent Schrodinger equation. If you make the zeta the imaginary time, then it's a Schrodinger equation. This reminded me of what was in Pasha's talk, actually. So Pasha's discussion, just that there are these heat equations arising, and I think you can, the wave function is very closely connected to the tau function. That's another question that I've put at the bottom, which I'll just come to in a second, and then I'll finish. I really will finish. So yeah, so this is not really a new result. As they point out, it's equivalent by a point transformation to what's called the Painleve-Kolodjoe correspondence, or the quantum Painleve-Kolodjoe correspondence, which is if you take the Hamiltonian for P6 and you write it in elliptic form, in the sort of inner Zemtsov Kolodjoe-Moser form of P6, which and then if in a sense, if you quantize the classical Hamiltonian, then that gives you a sort of Fokker-Planck or Schrödinger equation with an elliptic potential. And if you undo the point, do the point transformation that takes you from the rational form of P6 to the elliptic form of P6, then this heat equation here will be equivalent to that sort of quantum Painleve-Kolodjero form of Black's pair for P6, which was Zabrodin and Zotov, and I think Silimanov also had a version of it. So anyway, there is a heat equation for the wave function, and that to me suggests. Now, then this is the last point that I'll just make for discussion, is that, okay, I looked at the CFT formulae, but from my understanding from Sato theory, really the wave function should be, at least if we're talking about the 2x2 system or scalar Lax for Painleve, the wave function should be a ratio of tau functions up to an exponential factor. So, so really, if there should be, there should be a heat equation for the tau function as well. I'm guessing in the Painleve case as well. Okay, so maybe that's just a very confusing way to end the whole discussion, but or my part of the discussion. But anyway, I hope that that's given you some food for thought, and I hope you'll have some questions or some comments or some disagreements or some things to say. But thank you for listening. Thank you for listening to me, and thank you for inviting me to speak. Thanks.
Well, I actually have some general observation that here you were discussing possible. Well, first, thank you. It was very interesting. But before you were discussing, so you discussed the relation between possible relation between Painleve solution of Painleve equations and elliptic functions.
Mm-hmm.
And of course, in this, there's especially since you observed that Painleve 6 admits this kind of heat equation form.
Mm-hmm.
Because Painleve 6 is a bit special in this respect, because it is kind of elliptic in a hidden way.
Yes, true. True.
Because you can, and in fact, this is kind of what I wanted to say, because like there's another way that we can consider elliptic function as related in the context of Painleve equation, and then in this case is to start from P6, and it has this non-autonomous Kolodjero potential.
True. Yeah, in a sense, you could say perhaps it's doubly elliptic in a sense.
Yeah,
it's like
because the spectral curve has genus 1, but in that case you can also bring the problem into some elliptic form.
That's true. It's got a hidden elliptic symmetry in a sense. Yeah. And that's a very nice observation. That's a nice way to think of it. Yeah.
And in fact, and then I would want to raise kind of a question that I think it's rather relevant in this context, because in that case, there is also, we studied this with Pasha Gavrilenko and Harini Desiraju, the generalization to this sort of cases of the Kiev formula. But in this case, the tau function is not really this conformal block, because there's an extra factor which is written in terms of theta functions. But these are theta functions that depend on the transcendent itself. So it's some very bad object, because theta function of the Painleve transcendent for that case.
Yeah.
And so the point is rather like, I think an interesting open question there is how to study possible poles of the transcendent starting from those formulas in this general case. And I think this is kind of related also to this discussion.
But sorry, which models was that? Where you found these extra factors with theta functions depending on transcendence?
So if you just consider the tau function for Painleve 6, but the elliptic form of Painleve 6.
In the elliptic form.
The time is the modular parameter.
Yes. Yeah.
And then you have this Weierstrass potential.
Yeah.
So if you do that, then the tau function in the one that generates the Hamiltonians is no longer this just the conformal block or the Fredholm determinant, but you have an extra factor which is θ1 of the transcendent. From the geometric
point of view, it comes from the change of variables, essentially, the change of the point transformation.
Yeah, well, we don't find it that way. From the geometric point of view, it comes from defining bundles over higher genus surfaces. So in this case, you have some extra data that you have to specify just for the Lax matrix. This because the Painleve transcendent is the 0 of the 1-2 element of the Lax pair. So these are the theta functions take value at this 0. So it's kind of a divisor specifying this.
I guess. I see. Okay. That's very interesting. Yeah, I mean, I think the way that Kant suggests and Dornitz suggests is just to start from this rational form of the heat equation for P6, and then just do coalescence limit to the other ones. That's what they say. So I didn't. Yeah, I didn't try to sit down and do that yet, but it shouldn't be a difficult calculation, because you just you just do all the right scaling as in ints, and then it should just drop out. But yeah. Thank you. No, that's a very nice nice point, actually, about P6 being extra extra elliptic. Yeah, no, I've always found that very beautiful, this way of writing P6, but to really understand how it but I mean, also in a sense it's very important, because it's one way to sort of generalize naturally to high order or high dimensional, like Colodro type, Moser type, and so on. So actually understanding what all the solutions look like in this form is probably quite essential, because the general technology exists in the autonomous case for those systems. All the theory of like Hamiltonian reduction and even the integration is quite tricky in those elliptic Colodro Moser models, but I mean, if you try to translate them, wait a sec. If you try to translate them into rational form, do you get? Is it a natural thing to do? I'm not sure.
That I'm not Well, we never tried to do this because we were
Mm.
concerned with the general solution.
Yeah. Mm-hmm. Yeah.
But in fact, that's another point, that if one is able to grasp the meaning of these formulas for the transcendent, because for the tau functions they're rather clear, but because you have this extra factor, you don't know any longer how to get the transcendent directly from the tau function.
Mm.
That's kind of the main issue.
Yeah.
Because you can't write just because this extra factor contains the transcendent. You can't just write anymore that the transcendent is this logarithmic derivative.
No.
But these formulas hold also for higher rank non-autonomous calogero.
Yeah.
So that would be kind of, one is able to already grasp this 2x2 elliptic Painleve case, then also the higher rank non-autonomous calogero.
But I think it's even in the autonomous case. I mean, I'm not an expert on it, but I think, isn't it that somehow when you talk about, say, integrating the elliptic, say, let's just say elliptic calogero.
Mm-hmm.
So if we go to the rational case, like the simplest case, then the problem is literally, we know from Moser, we just have to diagonalize Hermitian matrices or something, right? So, but isn't it the case that really, if you want to say what's the solution of the elliptic calogero, you have to basically say it's just given by the zeros of some theta function, which is a cover,
Yes.
n-fold cover of an elliptic curve. So
Yeah.
So in a way, it's the solution is extracting the roots of the theta, in a sense, extracting roots from a theta function,
Yeah.
rather than diagonalizing a matrix. So it's you can see already in the autonomous case what the difficulty, somehow, where the level of difficulty is. But
well, actually, in this case, they're given by the zeros of the conformal block, basically. It's kind of the same story, but it's almost as if you're generalizing the zeros of these theta functions to zeros of the tau function.
Okay. Very nice.
Actually, can I make just a very small comment, because I feel a little bit guilty. Maybe I gave the wrong message when I gave my talk.
Oh, okay. Did I get the wrong end of the stick?
No.
I'm sure
Because,
that's my fault.
No. When
La colpa è mia. Non...
No. But of course, in Italian, it would be much easier to express myself. No, when we were talking about...
Possiamo anche farlo in italiano se vuoi, ma per gli altri non va bene.
Well, Fabrizio would be okay, but then other people, no. We have to stick with English. But yeah, anyway.
Scendiamo in inglese, sì.
Yeah. No, I just wanted to say that, so you as you were saying, so originally Kiev formula is for the upper part of the...
Yes.
But then later there was some very nice work by other people for the lower part as well.
Right.
And they also have some explicit formula. This is by Bonelli, Lisovi, also Mariosci, Sciarappa, Tanzini, and also by Itz and Lisovi, and the name that I never remember, which starts with P.
It's all right. Yeah. Okay. I just don't know the literature.
Yes, yeah. I just wanted to. Yeah. So
okay. Pavlo sent
Pasha
sent it
some
also.
references. Yes.
Okay.
No,
so what is the part that you don't understand for the lower level then? It's exactly...
Well, now I know that there have been some development, but for example, in the upper part, when we do the expansion on t equals 0, right? Everything, you know, it's convergent, and you know, this is a well-defined function, like on the full complex t plane, right? This is convergent anyway. But in the lower part, the expansion that they are, and also in the upper part, we have this coefficient b.
Yes.
With conformal blocks that we can really write like they are equal to something. We have like
okay. So it's convergent expansion. Sorry, that's the point.
Yeah, and but when we go down, they only have expansion at t to infinity, which is divergent.
Okay.
I think what you have in the, as far as I know, you don't really have a closed combinatorial formula for.
Yes, sorry. Yeah, it's yeah.
So
that's right. Yeah, sorry. No, I did understand it when you said it at the time, and I didn't really express it properly just now.
Okay, no,
yeah. It's the fact that it's convergent. That's the because for me that was the thing. When I was talking to Sasha, it's some years ago, was talking about really explicit, and I meant convergent. I mean, yes, convergent expansions, and okay, maybe the spirit of this program in the Newton Institute, everybody's doing asymptotic expansions, and I do a little bit of asymptotics, but it's not my main, you know, my main goal, my main research. So for me, if you do asymptotic series, then you probably say, well, asymptotics is just as good and it gives you whatever accuracy you want or so. But somehow, for me, as I don't know, just how I learned analysis, for me, convergence seems to be very important. so maybe, you know, convergent series is the sort of goal, is the ideal somehow. That's really, you're right. I did understand it when you explained it at the time, and I didn't express it today properly.
Okay. No, I just wanted to make sure, because it's
thank you.
work,
It wasn't.
I don't want to.
It was me not being very clear. Yeah,
but in the lower part, they can only get asymptotics and infinity, which are of course they are not convergent. But in some sense, they are not convergent, but they, I mean, you can think of them in terms of trans series in some sense.
Yeah. There's all. I mean, there's this great. I mean, I was amazed with Kostin's result of this Dubrovin conjecture. It's like incredible what he did. Yeah, I think he made it seem so easy, but proof of Dubrovin conjecture. But anyway, thank you. Thanks.
Although, even though the lower part series that one gets from gauge theory or CFT, they are asymptotic series. And there is some recent results where you just get Fredholm determinant for P2.
Yeah.
No,
there.
Yeah. But in that case, this is by Arenit Desiraju, but in that case, what is missing is instead the other part. The expansion that one gets is not nice, as in the case of the upper diagram. But in that case,
is that not because I know there have been formulae for P2 for some special solutions. So now is this the general solution that's done?
Yes, it's
for yeah. That's right. Okay, that's good.
For the special solution, it is possible to get the series, but for the general solution, there's technical problem to the nature of the Riemann-Hilbert problem and functional spaces. But well, the determinant is complicated, but it's like some explicit operator given in terms of parabolic cylinder.
Yeah.
So in that case, you don't have the series expansion, but the expression is kind of non-asymptotic. It's some well-defined object.
It is. Yeah, that's good. Was that who? Sorry, who was that? Was that the student from CISA? Because I think I
Yeah,
saw.
yeah.
Yeah, I think I found the PhD thesis just the other day. So but
okay.
I think I downloaded it and thought, right, I must read this now. But yeah, great, thank you. Yeah.
Thanks for the talk. So I wanted to ask one question. So you told this general equation is Painleve 34. I have tried to Google what is it, but maybe I don't understand. So I thought that any Painleve equations are, after all, reduced into one of Painleve 1 to Painleve 6. So
Yeah.
what is the meaning of this Painleve 34 in this
Oh,
context?
right. Okay. No, it's so Painleve 34. I can I can write it down if you like. That's because I have this thing. If my pen is going to work again, let's see. So P34 is this equation. And it's related to P2 by this Mura. So just no, I forget if it's with the should be that, yeah. So and then what's the inverse? The inverse is no. Yes, that's right. Yeah, I think it's this. So the L is just the shift of the parameter of P2. So the probably percent to it's probably I probably didn't get it quite. I think I missed the half of Z somewhere in one of the formulae, but anyway, so there's basically a one-to-one correspondence between solutions of P34 and P2. It basically comes from the Mura map of KdV. So P34, if you start with KdV, so then I can probably get the factors all right. But if you start with KdV and then you take U is something like T to the minus 1/3 W, no, T to the minus 2/3. That's right. So up to some factors, basically, then the scaling reduction of KdV gives you P34, whereas if you do this, and if you do the same scaling reduction for mKdV, I mean, up again, there's some choices of signs and so on. So you take V to be again. So again, this is all up to some scaling factors, which I'm not going to get correct unless I sit down and work them out. Right. So, but wait a sec. It's F. W. Yeah, sorry. I think
but maybe idea is clear. So.
Anyway, you get the idea. So it's just a one-to-one correspondence. But the point is that the point is that in terms of the Hamiltonian theory, then basically this W, yeah, I think I may need to put a Z onto there, but anyway, the point is that basically this W is basically like the second logarithmic derivative of tau up to some factors. Whereas the P2 is like is like the ratio of two tau functions, right? It's like two shifted tau functions, or the difference of two Hamiltonians is the solution of P2 y, right? Do you see what I mean?
Yes.
So it's just somehow the tau function or the Hamiltonian gives you directly the solution of P34, whereas in order to get the solution of P2, you need to take two of them. That's all. Yeah.
Okay. Thank you. So then maybe I misunderstood what are the names of these equations. So what is this general equation which gives Painleve 4, 2, and 1? Does it belong to Painleve classification or not?
Well, it is. I mean, it is just Painleve. It is just the Painleve 4 sigma equation, but it includes extra parameters. So they've just which you can remove by scaling, but what by setting them to 0. But what I'm trying to make the point is that if you solve this equation with all these parameters, then it gives you the solutions are all the solutions with all the parameters include all of those functions in one sort of multi-parameter form, as it were. That's what I was trying to. So just by, if you think of it as a multivariable special function with more parameters, then just by setting parameters to 0, you automatically obtain the solutions of the other Painleve equations, of the lower Painleve equations, if you see what I mean. Whereas normally, if you want to go from one Painleve equation to a lower one, you also have to scale the variables. You have to scale the independent variables. Do you see what I mean?
Yeah, yes.
So I don't know if it's an important observation or even a new observation, but I'd never seen it sort of done like this before, that somehow, you know, the same multivariable function includes all of these functions. So I always sort of think of going from one Painleve equation to another one as somehow very degenerate limit, but somehow if you just set a variable to 0, that to me, that doesn't seem to be very degenerate anymore. So, but it is obviously at the expense of having all these extra parameters in the solution, but it just means so, you know, in a sense they're redundant because you can scale them away. So obviously if you scale them away, that becomes more like a scaling limit again, but it's just, yeah, it's just, it seemed nice that you could have an analytic function of several variables, which includes all of those functions in one go, and includes elliptic functions. But that's all.
Is it more or less the same as to take, for example, Painleve 6 equation, then gather all these limiting procedures where we need to scale simultaneously coordinate and some parameter, and then include this scaling coefficients as parameters of initial equation, and I think after this we will also have this picture, then we can put one of these parameters to 0 and get a generic equation.
Yeah, I guess it must be equivalent. Yeah, I mean, just if you put more parameters into P6, so in principle you just need to add maybe a couple more parameters into P6, and then in principle you could get everything. So, but yeah, I think so.
This is basically one parameter for one degeneration procedure.
Possibly, except I mean it's a bit strange because we had let me see, so 5. Yeah, no, it makes sense, doesn't it? We had 1, 2. Yeah, it makes sense. Yeah, we should, in principle, we should be able to get everything by adding 2 more parameters to P6 and write down. So I mean, but I'm wondering whether this can be useful in any way. I mean, whether it's possible to do anything with the you know, with the conformal field theory formulae as well, but you just put one, you know, write one big equation, and then. But I guess the problem is whether when you when some parameters are set to 0, maybe things. But I mean that, yeah, I guess the point about these formulae is that they are definitely convergent for all parameter values. So that's the main advantage somehow. So whether it would be possible to get convergent formulae from starting from, let's say if we start from P, if we could do something for P5 and then degenerate to P4, you could maybe get a convergent expansion for P4, but from P5. Yeah, so I don't know. But in principle, yes, I believe it should be the case. I think you should be able to you should be able to do that. Just add it, because it's exactly as you say, it's the right number of parameters for each degeneration. There's up to P4. There's an extra parameter. So in principle, it should be possible to write down.
By the way, is your expansion always around a movable pole?
Yeah, this is also this is an expansion around a pole. That's the problem. Yeah, but the equation is well defined. It's just the sigma equation. So I mean, you could start with thinking about the sigma equation for P6 and extend it with some more parameters. Yeah, we just never got round to doing P6 and P5 as well, and P3. But in principle, it should. Yeah, I mean the expansion is always around the expansion that we've been using is just expanding around poles. That was the movable poles. That was the starting point. But the equation is well defined everywhere, so it's just.
Maybe it explains where everything works. Because if you want to expand around singularities, the type of this singularity changes when we generate the equation, and I don't know what happens with all these expressions. So at least in CFT, it's usually impossible to get this limit when we talk about kind of expansion around infinity. So we can get this limits for the we can get this limits for one type of expansion for the upper row of the diagram, but we cannot go down taking this limit. But maybe if you say about expansion around the movable pole, it probably doesn't know about what happens around zero, around infinity, and so on. So there are no problems.
Yeah, well, that's right. Yeah.
Sorry, this equation for tau that you wrote, where you had this A, I, J, K, which were integer, this was around 0.
It's around the 0 of the tau function, yeah.
Around the 0 of the tau function.
Yeah. So what we've done
so
is
the movable the poles. Yeah. Yes.
So what we've done is so that's a movable pole of the Painleve equation, yeah. But it's a movable 0. But what we've done is sort of, as I said, it's the philosophy is sort of to fix the pole to be at 0 and let the parameters, keep the parameters free. So if you like, the solution is specified to have a pole at 0 at the that's the sort of price you pay for having these this expansion, but I guess it's a small price maybe. Because obviously you can always write any solution, you know, with these parameters, with these X parameters. So.
Thanks.
Maybe that seems like a nice spot to stop the recording. And I mean, I can make Andy the host and
Yeah,
keep
yeah,
going if you
no,
want.
that's a good, that sounds good. Yeah.